I pause it when we're not actively going because I don't think Kaylin cares about listening to you work on homework. So I just only screencast when we're actually learning. Okay, so chapter 2, reasoning and proof. During our study of geometry, we're going to be using a system of logic. So logic is basically describing the rules of, in general, it's like philosophy, right? So describing the rules of like why something is right or wrong, how things are connected. For instance, if I say let's see, you are wearing a yellow jacket. I am a teacher, therefore the sky is blue. Like, what? Like, that doesn't make sense. You inherently understand logic because it has to follow. It has to make sense. Like, if I look outside and it's cloudy and I check my phone, it says it's going to rain, I'm going to take my umbrella to school, right? That makes sense. So it's reasoning. It's trying to solve problems. It has to make sense. It has to be like this like connected ideas. So this whole chapter is about reasoning, trying to like describe why we know this is true, what is the evidence to support it. My evidence when I was bringing my umbrella, my evidence to support it is the weatherman looked at the model and said, yep, it's going to rain. I looked outside, I saw water falling, and I said, yes, umbrella time. Right? So there has to be a reason for why we do it. So proofs is we're going to prove like, oh, how do we know that vertical angles are the same? How do we know that such and such is real? How do we know that's true? How can I prove it to you? So we're going to deal with proofs. Okay, so geometry, we're using a system of logic, a system of like rules, reasoning to prove different concepts, why we know certain things are true. So we're going to use general rules of logic, which is what we're going to start going over. Identifying and correctly using rules of logic is something you already know in algebra, and you kind of apply it in life. I hope you use your brain. I hope so. Like for instance, you're going to take a trip to Boston, right? How do you know what to pack? You have to think about it. You're like, okay, well, if it's summer, I know it's going to be hot and humid, I'm going to wear shorts. But if I'm going to go in February, you know it's going to be 8 feet of snow, so you'll wear pants, right? So you look at what you know and make a educated guess and like conclusion, hypothesis based on stuff you know. So we're going to be using these rules. We're going to be applying rules to basic geometric proofs. So conjecture and inductive reasoning. This first section is all about reasoning, logic 101. So if you're going to be taking a, philosophy course in your life, you'll learn about this again. If you're taking a logic course, because I'm actually in the middle of taking a logic course right now, and it's pretty cool. Anyway, conjecture. What is a conjecture? Do we know? Any ideas? Do you guys have an educated guess what conjecture means?
Conjunction, when things are together.
A conjecture is an educated guess. I asked you if you had an educated guess what conjecture means. Do you have a conjecture what conjecture means? Conjecture is an educated guess. So I look at the weatherman has very educated guess. He has these models and predictions. So I make a conjecture bringing my umbrella because you know what? It probably will rain if I bring my umbrella. Okay. Inductive reasoning. It's a reasoning that uses a number of specific examples to arrive at a prediction. So a lot of inductive reasoning is used by weathermen because they say, okay, I have all this history, when the atmosphere is dropping like crazy and these cloud covers and blah, 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 we know what's going to happen because it's happened in the past. Inductive, you have some examples and you're like, yep, I'm going to predict it. So I think Siri, if you have an iPhone or like the Android, Google, it will predict what you want to text back. All right, so this is inductive reasoning. Based on your texting habits, it will say, oh, hey, did you mean to say this to this person? And I'm like, no, quit telling me, sending hearts to everyone. I don't want to do that. So example 1. All right, so let's work on this. Eric was driving his friends to school when his car suddenly stopped 2 blocks away from school. Make a list of conjectures, educated guesses, that Eric can make why his car stopped. So you're driving to school, it stops 2 blocks away from school. Why is your car stopped? Do we have any idea?
Your engine broke.
So maybe you ran out of gas. Let's see. Someone said engine broke, so maybe your car broke down and died. Maybe you have a flat tire. That's an idea, right? So all of a sudden your car stops. Maybe it literally is flat.
Those dang kids started throwing rocks again.
What else? What about, like, could you stop for a red light?
Yes.
Yeah, that makes sense. So these are all reasons it could have stopped. We're making educated guesses. In science, we call these hypotheses. It's an hypothesis. We're trying to make an educated guess. We're not just throwing random stuff out. Like, we're trying to look at what happened and kind of guess why, not just random. All right, so example 2, the numbers represent below are called triangular numbers. Make a conjecture about the next triangular number. Okay, so what do we notice is happening from one to another? From going from 1 to 3, what happens?
2 more dots come out.
Yeah, I added 2 more dots. What about here?
Added 3 more dots.
Okay, what about here?
4 more dots. 5 more dots.
Okay, so we're trying to make a conjecture about the next triangular number. What will the next one be?
It's gonna add 7 to 6.
Okay, so 15 plus 6 is?
I don't know.
All right, so our conjecture, our educated guess, right? Our idea, we see a pattern emerging, so based on the past pattern, we can predict the future. So our conjecture is the next number is 21. See, you guys secretly, like, you can be good at logic sometimes. So being a logical person is good, right? You see patterns, you can extrapolate. On the ACT, SAT, they test you for extrapolation. So if you're being extra, you're going beyond. Extrapolation, you're going past the data points. So we just extrapolated. We went past what was given to us to predict something that was outside the boundaries, right? So we predicted the next one. We had our conjecture, we made an educated guess.
Oh yeah, the ERP they did one where it's like, what's the 20/100th one gonna look like?
We're gonna do something kind of like that. Speaking of it, we're gonna make a conjecture about the next item in a sequence. So we're looking for more patterns. So as I go from 20 to 16 to 11 to 5 to -2 to -10, let's see what's happening. So to go from 20 to 16, we subtracted 4. Let me zoom in a little bit. So we subtracted 4. To go from 16 to 11, 5.
6, 7, 8.
So what would the next one be?
9.
So we're subtracting 9. So what is -10 minus 9? -19. So our conjecture, our educated guess is it would be -19. Imagine if I came up and I was like, you know what, actually the next number is 15. You'd be like, what? That makes no sense. It doesn't make sense because we see a pattern and like your brain automatically knows what the next thing should be. So if something's like not making sense, it's not being logical. If someone is not being logical, they're making no sense, right? They're not following a set pattern. All right, let's try this one. What's happening here? Let's see. To go, so I could be adding 2, adding 8, adding, oh gosh, 30, oh gosh, oh geez, what's happening here? What about multiplying?
Yes.
Times 2.
Times 3, times 4, times 5.
Okay, so we see this is, so this one would be, did I write conjecture? I meant to write that. Hold on. Conjecture was -19.
Times 2, times 3, times 4, times 5, times 6, times 7, 10080.
So our conjecture is 10,080.
10,000.
Okay. Cool. So let's keep going.
How about, what's a good mnemonic for
Conjecture? Conjecture.
You got a conjunction at a train place. And then, you make an educated guess when the train's gonna arrive.
Sure. That's a good one.
And what's the other one called?
Inductive reasoning.
Inductive reasoning.
So we're using inductive reasoning right now to make a conjecture. So we're looking at the past pattern to make an educated guess what the next would be. Given points. What?
I think it's
I hope people are okay. I don't know. All right. Given the points P, Q, and R are collinear. Pause. What's collinear mean?
Collinear means
They're on the same line. Okay, so if I draw P, Q, R, they're all on the same line. See, I try to test you with vocab as we go. Okay. Joel made a conjecture, educated guess, that Q is between P and R. Is that true or false?
Maybe.
It's false. It does not have to be. The way I drew it, I was trying to mislead you. What happens if this is P, this is R, and then Q is over here? Then Q would not be between P and R.
It's still collinear.
It's still collinear, exactly. So it's not exactly true. So it's false because Q does not have to be between.
Do we have to write the whole thing out, or can we just say false on a test?
If I say explain, you have to explain.
Oh.
And 100% if I give you a problem like this, you're gonna have to explain. Because I don't choose guess. You have 50-50 shot of guessing true or false. No, I want to know that you know geometry. So, Q does not have to be between P and R for all 3 points to be collinear.
You have like 4 choices. It'd be like false, it'd be true.
Nah, I'm good. I'm good.
So.
I'm good. I'm good. Okay, so what I drew, this second one that I drew right here, this is called a counter example because I gave an example that showed why he's false. Counter example. So I'll do a more straightforward one. Here's an easy one. Okay. Everyone in this room is under 20 years old. That's my conjecture. Is that true or false?
That's false.
False. I am the counterexample. I'm not under 20. Ah, you see, logic. You understand. Let's come up with another one. Everyone in this room lives in Calabasas.
No.
False. I'm a counterexample. I don't live there. As long as you can come up with one thing that shows that it's false, one counterexample, one example that proves it, you can knock it out of the park. All right, so example 5. The table shows the total sales for the first 3 months a store is open. The owner wants to predict the sales for the 4th month. Okay, so first, what do we notice happening? From month 1 to month 2, we gain 1,000. What about month 2 to 3?
3,000.
Okay, so plus 3,000. I don't know if adding is the way to go. What if we tried multiplying? Multiply by 3. So if adding is not really showing a pattern, like maybe I'll add like 5,000. Yeah, so try multiplying by 3. So make a statistical graph that best displays the data, aka I'm gonna make some points on my graph. 1, 500, that's my first month. It's halfway between 0 and 1,000. 2, 1,500, that's halfway between 1,000 and 2,000. And I go over to month 2 and up to 1,500. Month 3, go over to 3 in the month data collected and go up to $4,500, which is right here. Interesting. So we see it's not a straight line. What's happening?
It's exponential growth.
It's a curve. Not necessarily exponential growth, but it is growing and getting faster and faster. So you may have learned about a parabola, maybe not, like a quadratic function. Anyway, it's not a straight line. It's growing faster and faster. So I'm not adding a constant number, so I'm multiplying by 3 every time. So what's my conjecture about the sales in the 4th month? How do I know how much I'll have? Exactly, times 3. So my conjecture is the 4th month of sales . 4th month of sales will be 3 times 4,500. Why is it doing this? Will be 3 times 4,500, which is $13,500. Awesome. right, let me pause here. There's questions. Don't move too fast. Maybe.
On the test, you will not put the 2 answers for us to pick out of, will you?
What do you mean?
Like, we will have to memorize the vocabulary and then write.
You do have to know the vocab.
Huh?
You have to know the vocab. If I say make a conjecture about sales in the 4th month, you have to know that conjecture means educated guess.
Okay, but like this won't like you.
I don't know what you're asking me.
You won't quiz us on the spelling and like and.
Well, as long as you do your best
Yeah,
guess,
okay.
because I mean, I know, like, I've had students before who, like, have learning accommodations, and some of them are, like, they can't spell, and that's fine. Like, I understand that.
Almost.
Just be, like, close, like, try.
Okay.
Yeah.
Got
All
it.
right. True or false statements. If a statement is true, it means that statement is always true. If a statement is false, it means you can find at least one counterexample. So counterexample, all it takes is one to prove it's wrong.
Uh-huh.
So we talked about counterexamples already, so now let's knock them out of the park. Determine whether each conjecture is true or false. Give a counterexample for any false conjecture. So, given angle 1 and 2 are supplementary angles, let's prove that 1 and 2 are both right angles. Is that, well, okay, so is that true? So we're told that 1 and 2 are supplement. So the conjecture is, guess what? My educated guess is, guess what? Both these are right angles. Are both of these right angles?
Not always.
No, it doesn't have to be, right? So we determine if it's true or false. This is false.
Yeah.
Why is this false? Can we come up with a counter example?
We could draw a thing that has a supplementary angle that's not 90 degrees.
Exactly. So if I come up with angle 1, let's say it's 50 degrees, what would angle 2 be?
It would be 40. Why?
130 degrees.
Wait, what? Oh, not
Supplementary, or, yeah.
90. Yeah.
So here, my counter example is the fact that, okay, well, I could give another counter example. So here I drew one, and I proved that, guess what? These two angles, 130 and 50 degrees, they add up to 180, and they're not right angles at all. Another way I could do it is I could say measure of angle 1 is 45 degrees. I could say measure of angle 2 is 135. And guess what? These angle 1 and angle 2 are supplementary. Yeah. And not right angles. So those are two different counterexamples. Right, so although I could have one specific example that makes the conjecture true, that makes that true, I just had to come up with one that makes it false. Okay, B, given points A, B, and C are collinear, is it always going to be true that B is between A and C? No, we already did this one. Trick play. Why is this false? Exactly. It can be anywhere as long as it's on the same line. Collinear just means same line, doesn't mean between. So a counterexample is, let's see, here's B, A, C. Notice they're all collinear. They're all on the same line, but B doesn't have to be between. And C, given n is a negative number, n squared is a non-negative number. Is this always true? Sometimes true? Let's come up. So what about, let's pick a negative number. How about negative 2? If I square negative 2, what's negative 2 times negative 2? 4, okay. Interesting.
No,
Interesting.
it's not
If I have a negative number and I square it, I'm taking a negative times a negative. Whenever you take a negative times a negative, it turns into a positive. So guess what? This is true.
That's true?
It's true. Can you think of a counterexample that makes it false? Can you think of a negative number when multiplied by itself, the negative doesn't cancel away?
It's a non-negative number. Oh, that means it's positive.
Yep.
Okay, sorry.
So this bottom example, I'm showing you if you have a negative times a negative, turns into positive. So I do have to come back up here. I forgot to write something. So a counterexample. So counterexamples could be a picture. You could have a picture that proves. Could be a graph. Could be a number, etc. Like literally it's just an example that proves that the conjecture is not always going to be true.
Okay.
Yeah. Okay. So let's pause here. 2.3 is conditional statements. So this section is all about how to form an argument, as well as what types of arguments are often used. So we talked about logic. So logic are the rules. So now we're going to talk about statements. So an argument, I said like, if the weatherman says the chance of rain is higher than 70, then I will bring my umbrella, right? So the thing I'm depending on, the argument, is the weatherman. Logic is the thing that tells me, yes, a weatherman is a good source to know from. But my conditional statement is if he says it's above a certain threshold, that causes me to have an educated guess, to make sure I bring my umbrella, to decide to bring my umbrella. Okay, so conditional statements is a statement that can be written in if-then form. If you buy a car, then you get $1,500 cash back. It's literally, do this thing, something comes back. If P, then Q. P implies Q. So if you go to a, car dealership and they have like, ooh, buy a new truck today, get $2,000 cash back, cool. So that's implying if you buy their truck, you get $2,000 back, whatever it is. All right, so the statement, the sum of two odd numbers is even. What would the if-then form be? How could I rewrite this? Because the statement would have been, you get $1,500 when you buy a car. Here, if you add two odd numbers, then the sum is even. If you add two odd numbers,
then the answer will be even.
Then the sum is even. Okay, this is where my handwriting gets really crappy. Okay, then the sum is even. Okay, two angles that have the same measure are congruent. How would I write this in if-then form? Any idea? Yes.
If two angles have the same measure, then they are congruent.
Beautiful. Could not have said it better myself. If two angles have the same measure, then they are congruent. Okay, so I feel like we're really leading in. So we've talked about how the whole goal of this chapter is to like prove certain things in geometry. Like this angle is the same as this one because blah, blah, blah. So we're prepping you for this. Okay, so this angle and this angle are congruent and we know they're the same angle, therefore blah, blah, blah. So we're constructing evidence, reasons why it's true. All right, I carry an umbrella on rainy days. So how would I rewrite this one, Maya? If.
If I carry an umbrella on days,
That'd be fine. I could say if it is rainy. If it is raining, then I carry an umbrella. And it really takes practice to just like be chill with this. Okay, so let's do some more practice. If-then statements are called conditional statements or conditionals. So the first thing we have is the hypothesis, right? The portion of the statement following the word if. So we're looking if that's true, right? So is it raining? Like I'm asking a question. My hypothesis, is it raining?
Yeah.
Are the angles the same? Are we adding two odd numbers? And then the conclusion is the portion of the statement following then. All right, so let's identify the hypothesis and conclusion of each statement. If points A, B, and C lie on line M, then they are collinear. So the hypothesis is the portion following if. So I write points A, B, and C lie on line M. This is my hypothesis because you're asking yourself, is this true? Do points A, B, and C lie on line M? Yeah. If that is true, we'll go to the conclusion, we'll do what it says. So I look outside and I say, is it raining? No, it is not raining right now, so therefore I will not bring my umbrella. If I looked outside and I said yes, my conclusion would be, have my umbrella. So this is a lot of times like computer science, people who program, if you work for Google, Microsoft, you have to be really good at logic. So this type of thing where it's like, okay, you have to be very clear, precise with your arguments and directions. All right, the conclusion is they are collinear. That's the conclusion. So if I can say all three are on line M, then I will conclude they're collinear. So the logic, the reason I can conclude this is because they're all on line M. So I have my evidence. I see they're all on line M. Therefore, like, I can draw the conclusion because I got evidence to support it. All right, B. The Tigers will play in the tournament if they win their next game. Ooh, this does not have the word then in it. Can I rewrite this in if-then form? Mm-hmm. Okay, how would I write it, Ashton?
If the Tigers play in if the Tigers win in their next tournament, in their next game, then they will play in the tournament.
All right, so if the Tigers win in their next game, then they will play blah, blah, blah. Okay, so the hypothesis is the Tigers win in their next game. The conclusion is they will play in the tournament. Okay, so sometimes like we're going from like super clear, I gave you the words if and then, to like, okay, now we have to rewrite it. Now, ooh, interesting. This is an interesting problem. So if x minus 3 equals 7, then x equals 10. So hypothesis, if x minus 3 equals 7, then I can conclude that x is 10. So that's chill. That's a chilly dog. All right. So let's write each statement in if-then form. A 5-sided polygon is a pentagon. Okay, so how could I rewrite this? If a polygon is a pentagon, then it has 5 sides. Huh? Wait, what'd you say? If a, I don't know what I said, I forgot. If a polygon did I say is a polygon is a polygon?
Yeah, no, you said if a pentagon is a polygon.
Okay. If a polygon is a pentagon, then it has 5 sides. I could also say, if a polygon has 5 sides, then it is a pentagon. Next one, math teachers love to solve problems. If you are a math teacher, what's our conclusion? Then
you love to solve problems.
Then you love to solve problems. Perfect. Perfect. All right. Yes.
The first one, can you also say if the polygon is 5 sided, then it is a pentagon?
Yep. That would be fine as well. All right, so the converse. So the converse is exchanging the hypothesis and conclusion of a conditional statement. So that's exactly what we just did. If Q, then P. Because before we're like, okay, if a polygon's a pentagon, then it has 5 sides. I could also say, if a polygon has 5 sides, then you're a pentagon. So you're just like flipping which one's your if. So if two angles have the same measure, they're congruent. If two angles are congruent, they have the same measure. You're saying the same thing. It's just different order. But you have to be careful because sometimes the converse isn't true, right? So what we're going to try is we're going to write the converse of each conditional statement. Then we'll comment on it if it's true or false. And if it's false, we give a counterexample. So we are putting everything together. So before I said, if a polygon's a pentagon, it has 5 sides. That's true. Pentagons always have 5 sides. If a polygon has 5 sides, then it's a pentagon. That's true. The only polygon that has 5 sides is a pentagon. That one's fine. What about B? If you're math teachers, then you love to solve problems. Yeah, that's true. That's true. Let's assume it's true. If you love to solve problems, then you're a math teacher. The converse is not true. There are people who love to solve problems who don't teach math. So that's why you have to be careful when you write the converse to make sure it will always be true. All right, so let's go ahead. Let's write the converse of each conditional. Then we'll say if it's true or false. If it's false, we'll give a counterexample. So the first one, if a person has a driver's license, then they're at least 16 years old. 100%. Yes. Welcome to California. That is true. The conditional is true. The converse. So if I flipped it, how would I write this if I flipped it? Exactly. If a person is at least 16 years old, then they have a driver's license. Okay, before you even say anything out loud, think to yourself in your brain, is this true or false? Is this converse true or false? Okay, so we think it's false. Why? What is your evidence? Is anyone 16 here that doesn't have a license? Yeah? Alright, so you don't have a license, right? Okay, so our counterexample, Maya. Maya is 16, she doesn't have a license. Heck yeah. Here's a better one. One of my friends in college was 19 when he first got his driver's license. Yep. So, I'll put a different name. How about like Ruth? This is a Jewish school. Ruth. Ruth is 83 and does not have a license. True story. You could just think of like one person in your life and that you could write them down. But I do know this old woman named Ruth from where I grew up, and she did not have a license. Thank God. She was blind, so she couldn't drive. That's why. That's really morbid. I'm sorry. Okay, B. If an angle measures 35 degrees, then it is acute. Then it is an acute angle. So the converse is, if an angle is acute, then it measures 35 degrees. Is that true or false? False. What the heck? What's our counterexample? I don't know. How about this one? This angle is 64 degrees, but it is acute. Perfect. All right. All right, so since we did not take a break after last one, so I'll pause here. All right, postulates and proofs. So something I want to mention, be very clear about. Oops, okay. So a theorem must be proven. So anytime we have a theorem, it's like a theory. You have to prove it. You have to have some reason to believe that it's true. So a theorem must be proven. So a theorem must be proven. Huh? 11 gone?
Oh, 11 gone. Okay.
Unless you look at the back of your book, it'll probably say that. All right, so a postulate. A postulate or axiom is a statement that is accepted as true. So we don't have to like fight it. We can just accept it as true. For instance, I mean, back in the 1200s, they thought the earth was flat. Now, the fact that the earth is a sphere is a postulate. We accept it as true. We also 100% know it's true from many, many, many different sources. All right, so in geometry, if we have a postulate, we'll accept it as true and we don't have to prove it. But this is what I recommend you guys do, is make some flashcards for yourself, because we need to know the different, rules. So through any 2 points, there is exactly one line. So line N is the only line through points P and R. There's exactly one line. There's not two. There's only one line that connects 2 points. So that's something like 100% has to be in your brain. You have to know. So we could make some flashcards at the end of class, just like flip through them. That'd be great. Through any 3 non-collinear points, there is exactly one plane. If I give you 3 points that are not together on a line, they're on a plane, there's only one plane that will contain all of them. A line contains at least 2 points. At least. So the difference between exactly and at least. Exactly is it's only one line through 2 points. That's it. There's no other right answer. There's not 0 or 2 or 5. There's only one line through any 2 points. But a line can contain 50 points. But it has to have at minimum 2. At minimum 2 points. It could have 3, 4, 50, 1,000, whatever. But it has to have at least 2 points. Because otherwise, if you only have 1 point, you're like, well, where's my other one? I don't know where my line is going. A plane contains at least 3 points. You have to have at least 3 to define your plane. If you have 2, that's only a line. If you have to have 3 to make it a 2-dimension plane. Also, that should not say plan. It should say plane. If 2 points lie on a plane, then the entire line containing those points lie on the plane. So it doesn't skew down or go around, nothing. That line is on the plane. If 2 points lie on a plane, then the entire line, that's what I just talked about, the entire line, the entire line. If 2 lines intersect, then the intersection is exactly 1 point, if they intersect. Guess what? If they don't intersect, there's no points of intersection. If they intersect, there's only 1 point. And that's why I had you guys do karate chop, because there's only 1 point between the 2 of you that were touching. And here's the thing. If you have a line and then another line that's lying right on top of it, that's not an intersection. That's just the exact same line, so that doesn't count. That's from Algebra 1. All right, so if you have 2 lines intersect, they only touch at 1 point. 2 planes intersect, then their intersection is a line. So we went through this yesterday in our little activity. We talked about it. Having 2 planes touch, it's literally going to be a line. I'm trying to think of a way to explain that. So that's what all this is saying. So these are the postulates, 2.1 through 2.5 postulates. So remember, a postulate is accepted as true. So all 5 of these things that I just said are accepted as true. All right, so we know we don't have to prove it. We know that through any 2 points, there's only 1 line. We know there's only 1 plane that goes through 3 collinear. All these things we know, we accept as true. We can use these to prove other things. So that's what we want to do. All right, so blah, 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 postulates, intersecting of lines, intersecting of planes. This is from chapter 1. Yes.
So non-collinear means they're on the same plane?
Non-collinear means they're not on the same line. They don't necessarily have to be on the same plane.
Oh.
But if I'm...
What was the thing that meant they were on the same plane?
a plane... So saying like 3... Okay, so it's kind of like what we just talked about with the conjecture versus the converse. So I say a plane contains at least 3 non-collinear points, but 3 non-collinear points don't necessarily are on the same plane.
Right.
Yeah, so you see what I'm trying to like be very specific about?
Got it.
I'm being really like petty right now because I'm trying to be exact. All right, example 1. Determine whether each statement is always, sometimes, or never true. If points A, B, and C lie in plane M, then they are collinear. Is that sometimes, always, never true? And what we want to do is we want to use the postulates. Here, we want to use the postulates from the previous page.
Sometime.
All right, so let's vote. Always, who thinks it's always true? If these are on the same plane, they're always collinear. Who thinks they're never true? Who thinks it's sometimes? Hey, tricked ya. Okay, so it is sometimes. The 3 points do not have to be collinear.
We've read the whole thing.
Why are you complaining? I literally wrote it for you, so you don't even have to think. You just copy pasta.
On the test, if you don't...
Let's focus on that when we get to it. Let's focus on the test, ... when we go over the practice test. Yeah. Because sometimes we go over examples and then later we're like, oh, that's how you shorthand it. Yeah. So for example, when you're talking about like, do I have to justify it? Hey, I gave you an out. I told you a counterexample could be a picture or a graph. Right? It just has to be clear justification. So notice that A, B, and C here are not collinear, but they're all on the same plane. So it's sometimes true because I could draw another one where they actually are all on the same line. So this is why it's sometimes true. It just depends where they are. Okay, there is exactly one plane that contains non-collinear points P, Q, and R. Is this always, sometimes, never true? What do we think?
Never.
It's always true.
Always true.
It's literally one of the postulates.
There's exactly
Through any 3 non-collinear points.
Wait, but can't there be non-collinear points between 2 planes?
Yeah, but it's talking about there's only one plane that contains the 3 non-collinear points. There's only one plane, so you could have like a point here, here, and there. There's only one plane that would contain all of them.
But what if they're on 2 separate planes? Can't they still be non?
So if you have 3, here. Put your fingers on the space, and you put one finger out as well. Put one finger out. Now, like, get closer so naturally. Here. Loosen up closer. Okay. There's exactly one plane that can touch all of them. Okay, so now, like, here. So maybe, like, there's another plane. I think there's only one plane that touches all of them. So, like, I can move my plane to match to have all 3, but there's only one that will actually have all of them. So I've been talking a lot with, like, planes like this,
What if
right?
you move this one here, and I move this one here?
Okay, so do something like this. Touch all 3 planes. That would, like,
There it is over here.
okay, so now it would be like this simple. He's moving his finger, it's not fair. But you see what I'm talking about? Like, if I could just have an infinite plane, like I could adjust it, and there's only one plane that would actually touch all 3. Okay, so the postulate, through any 3 non-collinear points, there is exactly one plane. It's literally the postulate.
I'm gonna fill that one.
You don't feel that one?
I'm gonna fill that one.
Well, you know the best way? Practice.
Yep.
You need to know the postulates. Yeah. Through any 3 non-collinear points, There's exactly one plane. Exactly one plane. All right, there are exactly 2 lines through points M and N. Is this...
Never.
Why?
Because you can't have 2 lines in one line.
It's never. There's only 1 line going through 2 points. There is exactly only 1 line going through 2 points. Awesome.
Always.
So this last one, plane ABC and plane DEC intersect at point C.
Yes.
So I have 2 planes intersecting.
Or no.
So if I had 2 lines intersecting, it would be a point.
Never.
But if I have 2 planes intersect at...
It's a line.
Planes intersect at a line. Okay, so never. 2 planes intersect at a line. Awesome. Do you guys need more time to write that down? All right, a proof. A proof is a logical argument in which each statement is supported by a statement that is accepted as true. So we're using our postulates, things we know are true, and we're working our way through to prove, something is congruent to something else. This is the measure, right? We're proving something. We're trying to reason why the following is true. So what we can do, the reasons why the statements that we're going to use, they can be definitions, they can be postulates, they can be theorems, etc. So proofs can be less formal, paragraph proofs, flow proofs. So it could be like a paragraph of words describing it. It could be a flow proof. I don't know if you've ever seen them, like the flow charts with the arrows, like that. It can be formal 2-column proofs. So we're going to be doing some 2-column proofs where it's like, here is the statement, this is the evidence for it, here's the next step, here's the evidence to prove why it's right. So that's a 2-column. Only 2-column proofs will be used in this class. All a proof really is justifying your argument. We're saying why this is true. Why can I do this? Why can I do this? And like justifying every single step. So Ashton, I feel like you're really going to love this because you keep asking about if you have to write everything. All right. So a theorem is a statement or a conjecture that has been shown to be true. All right. So it's a statement or a conjecture has been shown to be true. So a postulate is understood, we accept it as true. A theorem has been proven. A theorem is like, we know.
Where's the postulate?
What?
You said postulate.
Yes. So up here, the definition of postulate. Postulate is accepted as true. We don't have to prove it. A theorem has been proven, and now we can use it. So the proof process. How do we do proofs? All right, so we list the given information, and if possible, draw a diagram to illustrate it, just to help us. So the given is literally the hypothesis. It's what we're given. Of course, the given is what we're given. Then we state the theorem or conjecture to be proven. We create a deductive argument by forming a logical chain of statements linking the given to what you're trying to prove. So we give a statement, and then we give a reason why that's true. And then we have the next step. It's kind of like if you're making a cake. The difference is, when I'm cracking an egg, I'll be describing to you, I'm cracking an egg because eggs make it more fluffy. Like I have to give reasons why every single step instead of just like making a cake. I am baking it at 350 because if it is too low, it will not cook. If it is too high, it will burn. Right? So normally you don't justify the depth that we do in geometry.
I'm praying at 3 p.m. because that is when God comes out.
Wonderful.
And I can prove that. Because this is so many clicks.
Wonderful. All right, so here's our first one. Here's our first one. So we've talked about the midpoint before. So far the definition of midpoint that we've used. Oh my gosh.
Divided by 2.
All right, so the definition of midpoint we use so far, it divides a segment. I think we talked about this congruency. It divides a segment into 2 equal measures. What?
Kind of, like, just by looking at it, you can kind of tell there's middle 2 separate halves.
Yeah, but if I don't have the picture for you, if I say blah is a midpoint, you have to understand that it's equal to each side. Right. So if I say, oh, M is the midpoint between A and B, find the distance from A to M if M to B is 5. Like, oh, I understand the fact that, okay, midpoint means exact middle, so each side of it is the same, congruency. Understanding that. Okay, so what we want to do is we want to prove this theorem. I want to prove that this midpoint means that this length is the same as that length. I want to prove that. So our goal is to prove that M is the midpoint of P and R. Okay, sorry. We are given the fact that it's the midpoint. We want to prove that the lengths on each side are equivalent. So the first thing I want to do with my proof is list out the given. So, are we ready for our first 2-column proof?
Yes.
Follow along? Okay. So first, I'm going to write M is the midpoint of PR. The first line is always your given. M is the midpoint of PR. And so the reason for this, given. This was given to us. That's what I write, given. This is always the first line of your proof. You are restating what was written for you. Okay? So the next thing I want to do is use the fact that
Use a ruler.
the measure from P to M is equal to the measure from M to R. And the reason for this is the definition of midpoint. Alright, so that was the first thing I listed for you. I gave you the definition of midpoint. Midpoint divides a segment into 2 equal measures. Right, so I said equal measures. Equal measures. And so remember, if I don't have the line over it, PM literally means the measure from point P to point M. MR means measure from point M to point R. So if I don't have the line above it, it's the measure between those 2 points. And the definition of midpoint is it divides a segment into 2 equal measures. So if P to M is the same measure as M to R, because that's the definition of midpoint, guess what? My last step is state the result. This means segment PM is going to be congruent to segment MR. So segment PM, because I don't have arrows since it's a line segment, not a ray or line, it is a segment, is congruent to MR, the segment MR. And so the reason for this is the definition of congruent segments. I found the lengths of the segments were equivalent, but the lengths between the points were equivalent, and so therefore if the segments have the same length, therefore they're congruent. So this is the definition of congruent segments. Okay, so we're using givens, definitions. Let's pause here. Yes, 100%. This is to help you understand how to write proofs.
Scary.
Yeah. Okay. So now we're going to complete this proof. Given that angle 1 and angle 2 are right angles, let's prove that they are congruent. So what's the first thing we want to do whenever we write a proof? First step is we always write the given. The first thing we always write in a proof is the given. Under our statements, the first statement is always the given. Okay, step 1 done. Awesome. Okay, so I have the given. So, okay, so if they're right angles, this means that the measure of angle 1 is 90 degrees and the measure of angle 2 is 90 degrees. Okay, so it depends who, like, if you go to all the math teachers here, I bet you, like, we all do proofs a little differently. Because I hate repeating myself 50 million times. And so the way I'm going to do this proof, it's going to be annoying to me because it's like, I just said that. I just said that. It's just saying it a little differently. And it's like baby steps, right? If you go to Miss Kasif, she may use more steps than I do. Miss Ko may use even more. Like, it kind of depends. But the logic is all there. So we start with our givens. Then we try to use, like, definitions, substitutions. My reason for telling you this is, I'll be real. Sometimes I still struggle with proofs because I'm like, why? Why do I have to prove that? Like, I thought it was proven already. So I feel your pain and anguish, but we will persevere together. Like, let's do this, This is great. This is fine. Everything's fine. All right. Number 2. So we know they're right angles. Being a right angle means it has a measure of 90 degrees. So the measure of angle 1. So when I write the M in front, it means measure of. Measure of angle 1 is 90 degrees. And measure of angle 2 is 90 degrees. So this is from the definition of right angles. Because we're like, oh, what does it mean to be a right angle? Oh, it means having a measure of 90 degrees. Definition of right angle.
So we need to
I'll give you a list of proof reasons, okay? But it's not always going to be given, definition. It's always going to be given, and then it depends what you're trying to prove. Yeah. Yep. Okay. So if measure angle 1 is 90 and measure angle 2 is 90, then I can set the 90 degrees equal to each other because it's the same. Let me just do a little aside. Let me show you what I mean, okay? This is like not on your notes. So if I have like x plus 5 equals y, and I know 10 equals y, guess what? These are both y's. It's the same y. I can literally set those equal to each other. Coolio, see where this is going? Maybe, So I'm going to do, since this is 90 degrees and that's 90 degrees, I'm going to set measure of angle 1 equal to the measure of angle 2. Holy baloney. Oh my god. You know what I call this? Substitution. Substitution. Okay. So, interesting. If the measures are the same, you know what that means? That means angle 1 is congruent to angle 2. And this is from the definition of congruent angles. And if we go back through our notes in chapter 1, you will see definition of congruent angles means they have the same measure. Like, all of those definitions that are in chapter 1, we're going to be using them. Definition of congruent angles. Okay. And guess what? That is section 5. We have a question?
Yeah. So do you always know you're done when you get like that answer?
When we hit what we're trying to prove. So we know when we're done when we hit what we're trying to prove. We're trying to prove this guy, we hit it.
And then how do you know like
Practice. The only reason you know is practice. Yep.
because I would think that like would be done before.
Yep. 100%. There, you have to like. It just takes practice. You have to know. You only learn it by doing it. Unfortunately. Okay, so let's end the screencast here.